Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Motion and Static Non-Uniform Fields from paper Electromagnetic Theory. From this module, students, you may get to know about the following things. First, the relativistic motion of charged particle in static but non-uniform magnetic field configurations. Second, motions in a magnetic field with gradient perpendicular to the direction of the magnetic field leading to the gradient drift. Third, motion in magnetic field with curving lines of force leading to the curvature drift. We now study the nature of particle trajectories in a static but non-uniform magnetic field. Consideration of a non-uniform magnetic field is of interest in many areas such as magnetohydrodynamics, astrophysics and thermonuclear applications. Often, as in the case of interstellar and intergalactic space, the field is rather slowly varying so that the problem can be tackled perturbatively. We know that for a uniform and static magnetic field, the trajectory of a particle is a helix with uniform motion along the direction of the field and circular motion with certain radius of gyration in a plane perpendicular to the field. But slowly varying field, we mean that the distance over which the field varies appreciably in magnitude or direction is large compared to the radius of gyration of the particle, so that over one gyration the field can be taken to be nearly constant locally. The motion is then one of gyration with a radius and frequency that depends on the local value of the field. In the next order of approximation, slow changes occur in the orbit of the particle, which can be described as the drift of the guiding center. Let us first consider a spatial variation of the magnetic field B, which is a gradient perpendicular to the direction of the field. Let the gradient at the point of interest be in the direction of the unit vector n cap, so that n cap dot b is equals to 0. The particle has charge q, mass m and velocity v. Then, to first order, the gyration frequency can be written as omega b as a function of x equals to q divided by gamma m into b as a function of x equals to q divided by gamma m into b naught plus del b by del zeta naught into n dot x, which is further equals to omega naught into 1 plus 1 divided by b naught into del b by del zeta naught n dot x, where beta naught is the field at the guiding center and omega naught is the gyration frequency at that point. Since the direction of field is unchanged, the motion of the particle parallel to the field remains a uniform translation. Therefore, we consider modifications in the motion perpendicular to field only. Let V naught be the transverse velocity of the particle in the uniform field case and V1 the correction to it. Since the non-uniformity of the field is small, the magnitude of V1 is small as compared to that of V naught. So let us write V perpendicular equals to V naught plus V1 for the transverse component of the velocity of the particle. Then from the Lorentz force equation, we can write dV perpendicular by dt equals to E by gamma m into V perpendicular cross Bx equals to V perpendicular cross omega Bx. This implies that dV naught plus V1 by dt equals to V naught plus V1 cross product with omega naught into 1 plus 1 divided by B naught into del B divided by del zeta naught into n dot x. So on comparing the 0 and the first order terms, we obtain d V naught by dt equals to V naught cross omega naught, and d V1 by dt equals to V1 plus V naught into n cap dot x naught into 1 divided by B naught into del B by del zeta naught whole with cross product with omega naught. The first is the equation for the unperturbed motion. In the second only, the first order terms are retained consistently. So, V1 cross omega naught into 1 divided by B naught into del B divided by del zeta naught into n dot x being a second order term in perturbation is ignored. The solution of the problem in a uniform and static magnetic field is well known, and we have derived it earlier also. So, in the transverse direction, the solution is V is equals to A omega B cos omega B t into x cap minus A omega B sin omega B into t y cap, and xt equals to x naught plus A sin omega B t into x cap plus A cos omega B t into y cap. So, on taking the cross product of the above equations with omega b, which is a vector along the z direction, we have V is equals to minus omega b cross x minus x naught, and x minus x naught equals to 1 divided by omega b square into omega b cross V. So, in the present case, the unperturbed velocity is V naught, and the unperturbed position is x naught, and the unperturbed frequency is omega naught. The center of gyration of the unperturbed motion has been taken to be the origin, hence x naught equals to 0. So, on making the appropriate change in the symbol, we have V naught equals to minus omega naught cross x naught, and x naught equals to 1 divided by omega naught square into omega naught cross V naught. So, this implies that d V1 by dt equals to V1 minus 1 divided by B naught into del B by del zeta naught into n cap dot x naught into omega naught cross x naught and whole with cross product omega naught. So, presence of the inhomogeneous term 1 divided by B naught into del B by del zeta naught into n cap dot x naught into omega naught cross x naught cross omega naught leads to a term in the solution with non-zero average value Vg equals to time average of V1 equals to 1 divided by B naught into del B by del zeta naught into omega naught into time average of x naught perpendicular into n dot x naught. The rectangular component of x naught perpendicular oscillates sinusoidally with amplitude A and a phase difference of pi by 2. Hence, only the component of x naught perpendicular parallel to n cap contributes to the average. Thus, we can write time average of x naught perpendicular into n dot x naught equals to a square by 2 into n cap, and on substituting this value, we have for gradient drift velocity Vg equals to a square by 2 1 divided by b naught into del b divided by del zeta naught into omega naught cross n. Since del B by del zeta is the normal gradient of magnetic field in the direction of n cap, so del B divided by del zeta naught into n vector is equals to del perpendicular B. Also, omega naught plus B being parallel, omega naught B equals to omega naught B vector. Thus, the gradient velocity can be written in a dimensionless coordinate free form Vg divided by omega b into a equals to a divided by 2b square into b cross del perpendicular b. If the gradient is small compared to the field, that is a into mod of del b by b is much less than 1, this implies that mod of Vg is much less than omega naught a. The particle spirals rapidly while its centers of rotation move slowly in a direction normal to both the field and its gradient. The sense of drift as given by the equation above is for positively charged particles. That is, if the field is along the z direction and its gradient along the x direction, then the drift will be in a positive y direction. For negatively charged particle, omega naught has a negative sign, hence the direction of drift is opposite. Now let us see the qualitative explanation. The gradient drift can be understood qualitatively in the following way. As the particle circles around the guiding center, it passes through the region of varying field. For half the cycle, the field is greater than the average, and for the other half is less than the average field. Since the radius of gyration is inversely proportional to the field, for half the cycle the particle moves in a tighter than the average arc, and for the other half in a broader than the average arc, producing a net drift in the transverse direction. The curvature drift. The second type of field variation we consider is the curvature of lines of force. This type of variation also leads to a drift of the guiding center called the curvature drift. Consider a two-dimensional field. To be specific, let the field be in the xy plane. The unperturbed uniform field B0 is along the x-axis. In such a field, a particle spirals around the lines of force with radius of gyration a and velocity omega ba. For the field under consideration, the lines of force are curved with the local radius of curvature r, which is large compared to the radius of gyration. Therefore, the non-uniformity can be regarded as a small perturbation to the unperturbed motion. Physically, the first order motion can be understood as follows. The particle tends to spiral around a field line, but the field line, instead of being straight, curves off to a side. As far as the motion of the guiding center is concerned, this is equivalent to a centrifugal acceleration of magnitude v perpendicular square by r, which means a centrifugal force of magnitude m gamma v perpendicular square by r. The same effect would have been produced had there been an electric field, that is E effective is equals to gamma m by q r vector divided by r square v parallel square. This effective field is in a direction transverse to the magnetic field. Since the radius of curvature is large compared to the radius of gyration, the effective electric field is small compared to the magnetic induction. The motion is therefore equivalent to that in cross electric and magnetic field with E less than CB. This causes a drift with drift velocity c into E cross B divided by B square. Thus, the curvature of the lines of force leads to a curvature drift velocity Vc, which is given by Vc equals to E effective cross B divided by B square equals to gamma m by q r cross B naught divided by r square B naught square into V parallel square. So we emphasize that no actual electric field is produced. The effect of the force on the motion of the particle does not depend on the origin of that force. Thus, the effect is same had an actual electric field been present. The frequency of gyration is given by omega b equals to q b naught divided by gamma m. Using this expression, Vc can be written as Vc equals to V parallel square divided by omega b r into r cross b naught divided by r b naught. The direction of the drift is specified by the vector products in which r is the radius vector from the effective center of curvature to the position of the particle. Thus, if the field is along the x-axis and the lines of the fields are curving upwards so that the center of curvature is along the positive y direction, the drift velocity is along the z direction. This is true for a positively charged particle. For a negatively charged, the sign will be opposite because of the factor omega b. And the direction of the drift is independent of the sign of V parallel since it depends on the square of the velocity. An alternative derivation proceeds as follows. If the center of curvature is chosen as the origin of the system of coordinates, then in cylindrical coordinates the magnetic field has only an azimuthal component. Let us recall some of the relevant results from vectors in cylindrical coordinates and write a vector A in both cylindrical and Cartesian coordinates as A equals to Ax into x cap plus Ay into y cap plus Az into z cap equals to Ap into rho cap plus Aq A phi. The relation between components of a vector in cylindrical and Cartesian coordinate is A rho is equals to cos phi Ax plus sin phi Ay. A phi is equals to minus sin phi Ax plus cos phi Ay and Az equals to Az, which implies R is equals to rho into rho cap plus Z into Z cap and vector V is equals to R dot vector is equals to rho dot into rho cap plus rho phi dot into phi cap plus Z dot into Z cap, and A vector is equals to V dot vector equals to R double dot vector equals to rho double dot minus rho phi dot square whole into rho cap plus 2 rho dot phi dot plus rho phi double dot whole into phi cap plus z dot z cap. Since in a magnetic field energy is constant, Lorentz force equation takes the form gamma mv dot vector equals to q v vector cross b vector, which implies rho double dot minus rho phi dot square into rho cap plus 2 phi dot into rho dot plus rho phi double dot whole into phi cap plus z dot z cap equals to Q by gamma m into rho dot into rho cap plus rho into phi dot into phi cap plus z dot into z cap whole cross product with b naught phi cap, which is further equals to rho dot rho cap plus rho phi dot phi cap plus z dot z cap whole cross product with omega b phi cap, which implies rho double dot minus rho phi dot square equals to minus omega b z dot, and 2 rho dot phi dot plus rho phi double dot square equals to 0 and z double dot equals to omega b rho dot. We are looking for the lowest order solution for which rho is equals to r, which implies that phi double dot equals to 0 and phi double dot equals to 0 equals to some constant equals to v parallel divided by r, which implies that z dot equals to v parallel square divided by omega b r. Combined curvature and gradient drifts. Consider the gradient drift that accompanies a curvature drift in cylindrical geometry. The magnetic induction is B equals to B phi into phi cap equals to B naught phi cap, and in free space del cross B is equals to 0. So from the z component of this equation we'll get del cross B, the z component, equals to 1 divided by rho into del by del rho into rho B phi minus del B rho divided by del phi equals to 0. So this implies del by del rho into rho B phi equals to 0 implies that B phi equals to B naught by rho, where B naught is some constant. Therefore, del perpendicular B is equals to del by del rho of B naught by rho whole into del cap equals to minus B naught by rho square into rho cap equals to minus of B phi by rho square into rho vector, which implies that B cross del perpendicular B by B square equals to minus of B cross B rho vector by rho square divided by B square equals to R vector cross B vector divided by R square B. Here we have used the lowest order solution, that is rho equals to r, the radius of curvature. The gradient drift velocity Vg takes the form Vg equals to a square omega b by 2 into b cross del perpendicular b whole by b square equals to half of v perpendicular square by omega b r whole into r vector cross b vector by r b, where v perpendicular is equals to a omega b. Now we can combine the two expressions for Vg and Vc and obtain the total drift velocity Vd equals to v parallel square plus half v perpendicular square by omega b r whole into r vector cross b vector by rb. For a charged particle in thermal equilibrium, mean energy is 3 by 2 kT, and the square of each component of velocity is kT by m, where k is the Boltzmann constant and T is the absolute temperature. Since V perpendicular has two components, so V parallel square is approximated to half of V perpendicular square, which is approximated to kT by m. Hence, the two terms contribute to the drifts with similar magnitudes. Substituting for the velocities in terms of the temperature from above and using the numerical value of the charge of electron and other constants for a singly charged particle, we obtain Vd in terms of cm by second equals to 172 T with units Kelvin divided by r in meters and b in Gauss. Particle drifts implied by the above are troublesome in thermonuclear machines designed to contain hot plasma. For the thermonuclear reactions to initiate, the hot plasma must attain sufficiently high temperature and stay confined for sufficiently long time. Because of the drifts, the plasma will leak out of the walls and will not remain confined. Now let us see about the motion parallel to the field, that is adiabatic invariance. The various motions we have discussed so far have been perpendicular to the magnetic lines of force. These motions caused by the electric field or by the gradient or curvature of the magnetic field arise because of the peculiarities of the Lorentz force. In particular, the fact that the force due to the magnetic field is perpendicular to both the field and the velocity. This lead to drifts which at first sight might be because of counterintuitive. To complete our study of the motion in magnetic field, we now consider motion parallel to the magnetic field. It turns out to be slowly varying fields. A powerful tool is the concept of adiabatic invariance. An adiabatic invariant is the property of a physical system that stays constant when changes occur slowly. In thermodynamics, an adiabatic process is a change that occurs without heat flow and slowly compared to the time to reach equilibrium. In an adiabatic process, the system is in equilibrium at all stages. Under these conditions, the entropy is constant. In mechanics, an adiabatic change is a slow deformation of the Hamiltonian where the fractional rate of change of the energy is much slower than the orbital frequency. The area enclosed by the different motions in phase space is an adiabatic invariant. In quantum mechanics, an adiabatic change is one that occurs at rate much slower than the difference in frequencies between energy eigenstates. In this case, the system does not make transition between energy states so that the quantum number is an adiabatic invariant. The old quantum theory was formulated by equating the quantum numbers of system with its classical adiabatic invariant. This determined the form of the Bohr-Sommerfeld quantization rule. The quantum number is the area in phase space of the classical orbit. Since the magnetic field is divergence free, that is del dot B is equals to 0, there is a small radial component of the field in addition to the z component. For simplicity, we assume cylindrical symmetry. Suppose that a particle is spiraling around the z-axis in an orbit with small radius. So at z equals to 0, the field strength is B0 and the transverse velocity of the particle is V perpendicular naught and the parallel component is V parallel. Since the energy of the particle is fixed at any position along the z-axis, so V parallel square plus V perpendicular square is equals to V parallel naught square plus V perpendicular naught square equals to V naught square. So if we assume that the flux is adiabatic invariant, then V perpendicular square by B is equals to V perpendicular naught square by B naught. So on combining these two equations, we'll get V parallel square equals to V naught square minus V perpendicular square equals to V naught square minus V perpendicular naught square into Bz divided by B naught. As the particle proceeds along the positive z direction, the magnetic field increases and hence V parallel decreases. If Bz increases enough, eventually the right hand side of the equation becomes 0 Also, Bz increases, the radius of gyration decreases. This means that the particle spirals in an orbit with decreasing radius of gyration, converting more and more of its translational energy into rotational energy until its axial velocity vanishes. Then the particle turns around till spiraling in the same sense clockwise or anti-clockwise and starts moving in the negative z direction. The particle is reflected by the magnetic field as depicted in the diagram given in the. Then particle turns around, still spiraling is in the same sense clockwise or anti-clockwise, and starts moving in the negative z direction. The particle is reflected by the magnetic field as depicted in the diagram given. We have thus what is called a magnetic mirror. The above equation is a consequence of the adiabatic invariance of P perpendicular square by B. So, in this particularly simple case, the invariance follows directly from the Lorentz-Force equation. The field must be divergence free, that is del dot B is equals to 0, and in cylindrical coordinates the divergence has the form del dot B equals to 1 divided by rho into del by del rho of rho B rho plus 1 by rho del by del phi of B phi plus del by del Z of Bz equals to 0. Since field has radial and axial components, 1 by rho into del by del rho of rho B rho plus del Bz by del Z equals to 0, provided del Bz by del Z does not vary much with rho. So we have rho B rho is equals to minus of integral from 0 to rho of rho del Bz by del Z into d rho equals to minus half rho square into del Bz by del Z. This implies B rho is equals to minus of half rho into del Bz by del Z. Write the LHS and RHS of the force equations in cylindrical coordinates. Equate the Z components, that is Z double dot equals to Q divided by 2m gamma into rho square into phi dot into del Bz by del Z. In the present notation, rho square phi dot equals to minus of a square omega b whole naught equals to minus of v perpendicular naught square divided by omega b naught, which implies z double dot equals to minus of v perpendicular naught square divided by 2b naught into del bz by del z. So this implies v parallel square equals to v naught square minus v perpendicular square equals to v naught square minus v perpendicular naught square into bz by b naught. The magnetic mirror. The mirror effect will only occur for particles within a limited range of velocity and angle of approach. As we have seen above, a magnetic mirror is a configuration of magnetic field lines in which a charged particle is reflected from a region of high magnetic field to low magnetic field. Magnetic mirrors are made up of specialized electromagnets designed to create a highly inhomogeneous field. Large magnetic mirrors have been used experimentally as a mean of plasma confinement. One major application on which a lot of research is being carried out is to confine the hot, electrically charged plasma inside a fusion reactor to generate fusion power. The concept of plasma confinement by using the idea of magnetic mirror was proposed in mid-1950s. By late 1960s, magnetic mirrors confinement was considered a viable technique for producing fusion. Magnetic mirror also play an important role in other types of magnetic fusion energy devices such as tokamaks. Magnetic mirror also occur in nature. Electrons and ions in the magnetosphere, for example, will bounce back and forth between the stronger field at the poles, leading to an Van Allen radiation belt. Now let us see the example of magnetic bottle. A magnetic bottle is two magnetic mirrors placed close together. For example, two parallel coils separated by a small distance, carrying the same current in the same direction, will produce a magnetic bottle between them. An image shows how a charged particle will corkscrew along the magnetic field inside a magnetic bottle. The particle can be reflected from the high field region and will be trapped. Unlike the full mirror mechanic, which typically had many large rings of current surrounding the middle of the magnetic field, the bottle typically has just two rings of current. Particles near either end of the bottle experience a magnetic force towards the center of the region. Particles with appropriate speeds spiral repeatedly from one end to the region to the other and back. Magnetic bottles can be used to temporarily trap charged particles. It is easier to trap electrons than ions because electrons are so much lighter. This technique is used to confine very hot plasma with temperature of order of 10 raised to power 6 Kelvin. In a similar way, the Earth's non-uniform magnetic field traps charged particles coming from the Sun in the donut-shaped regions around the Earth called the Van Allen radiation belt, which was discovered in 1958 using data obtained by instruments aboard the Explorer-1 satellite. So students, let us summarize what we have learnt in this module. In this module, we have studied the relativistic motion of charged particles in magnetic field. Motion in static but non-uniform magnetic field has been studied for various types of non-uniformities. Motion in a magnetic field with gradient perpendicular to the direction of magnetic field has been described, leading to the gradient drift of the particle. Next, the motion in magnetic field with curving line of force is studied, and this leads to the curvature drift. Both types of non-uniformities can be present together, and it has been found that the two terms contribute with similar magnitude. Finally, motion along the direction of a slowly varying magnetic field has been studied, and the concept of adiabatic invariance has been introduced to you. Lastly, motion along the magnetic field has been analyzed by employing these adiabatic invariants. Use of such a configuration as magnetic mirrors and magnetic bottle has also been discussed. Thank you.